Okay, so let's continue with our proof. So we were saying that in the special case when f of x equals 1, so this guy is 1, so this integral just stays the same, but instead of f of u plus x we have 1. But now this integral should be equals to 1, so that's probably detail 2. Detail 2. Just put it in, I think I put it in orange. So detail 2. That will be another thing we have to check. Okay, but those are little details that are easy to do. Okay, I don't want to start doing that because you might lose the main point of the proof. So since this is equals to 1, now I can multiply both sides times f of x, multiplying both sides times f of x. So we get f of x equals 1 over pi integral o minus pi over pi. So I could put the f of x here, right? F of x, but then the f of x, I can put it inside the integral because it doesn't depend the u. So I can write sine n plus 1/2 u over 2 sine u over 2 times f of x du. Okay, so we have that ready. Okay, and now we're gonna subtract. So subtracting let's call a start and double star. So subtracting well, no, let's not call it a star. Sounds kind of weird. Let's call it oh no, I had used this already. One. Did I call any equation 1? No. Okay. So let me make this smaller. It's making bigger and bigger. So subtracting, let's call this one 1. And this is 2. Subtracting 1 minus 2. We get this Snx minus f of x equals okay, let me make it smaller like this. Then we will have 1 pi and 1 pi is the same, right? So we can factor 1 pi. Now there will be the integral minus pi pi minus the integral minus pi pi, the same thing. Now these two guys are the same. The Dirichlet kernel is the same, right? So Dirichlet kernel, Dirichlet kernel, Dirichlet kernel, Dirichlet kernel. So I can factor that one, sine n plus 1/2 u divided by 2 sine u divided by 2, right? And then I will get fu plus x minus f of x dx. Okay? Oh wait, the not the x but the u. Not the x but the u. Sorry, I have a typo in my notes. Du. Okay, so you are going to integrate with respect to u, but this function still has x, so that makes sense that this function on the left is going to be in terms of x, because the du is going to disappear because it's after the integration. Okay, but now notice something really interesting here. So let's make a definition. Let's say g of u let's put it, sorry, let me put it here like that. Yeah. So let hold on a second, my pen is okay. So let g of u, let's define this just for notation. Let g of u equals definition. Let's just for simplification, let's call this guy g of u. This is gonna be g of u is gonna be f of x plus u minus f of x over sine of u divided by 2. Okay, so let me put this guy, we're putting this guy over this guy, and we are calling it g of u. So let me call, so let me say if we let g of u be in that, so we will write 1 over pi integral between minus pi and pi sine of n plus 1/2 u divided by 2 sine of u over 2. Oh, sorry, no, this one, no, this one doesn't go. So this guy over that guy is gonna be g of u, so I call it g of u du. Okay. Now does it look familiar? This is sine of something times g of u, right? So this is the integral between minus pi and pi, 1 over pi sine u. So this is, I call this guy, I could call this guy the inner product of g with let's call this phi sub n. No, let's call it like this. No, yeah, let's call it like that, just to be clear. G of u comma sine n plus 1/2 u. Okay, so I'm trying to not being so, I'm trying not to write so many details, but also trying to be clear. So I hope I'm doing it. Okay, so this is, look at that. So Snx minus f of x equals the inner product of u comma sine n comma n plus 1/2 u. Okay, and then we're gonna use an important statement. We notice, that's detail 3. We notice, let me make this bigger. We notice that the functions let's call it phi sub n of u Oh, sorry, I just noticed a mistake here. I was using capital N and now I'm using a small n. Oh my goodness. It looks like capital N. So this sign should be capital N. I apologize. Capital N. Capital N. And this should be capital N. And this should be capital N. And this should be capital N. And there you go. So what happens is that I start using one book, but then I like better the proof of the second book. I think it's just easier. Yeah, use so this proof that I'm using is Strauss book. So it's in the bibliography. Okay. So yeah, I kind of like the notation. That's the notation we have been using. So I'm changing it. I'm changing his notation a little bit. Okay. So I think that's good. So we notice that the functions phi sub n of u, that is sine n plus 1/2 u n equals 1, 2, 3, 4, and so on, form an orthonormal basis. For an orthogonal, non orthonormal, or form an orthogonal basis. You are expert on this, so that's what I like it better. Form an orthogonal, no basis, for an orthogonal set on the interval 0p. Okay, they are also orthogonal. They're also orthogonal on the interval minus pi. Okay, so this is, let's call it detail 3. This is another detail I'm not gonna do, but it's an easy detail, good for homework. Okay, so we are saying this difference is the inner product of these two guys, where g is this function. And now this turns out that with this guy I can make an orthonormal set, or orthogonal set. Okay, so why is that good? That is good because we can use the Bessel's inequality. Therefore, we can use Bessel's inequality. So that means that, let's write here Bessel's inequality. What is Bessel's inequality? Bessel's inequality says that if phi1, phi2, phi3, and so on are orthogonal, or form an orthogonal set, in an inner product space B, then we have the following inequality, and it says, the inequality says the sum on n equals 1 to infinity of the inner product of G with phi sub n squared over the norm over the phi sub n squared is less or equal than the norm of G squared. So what is that useful? We'll see it right now. So this is an orthonormal set, and turns out we can apply this inequality. So by direct calculation, you can calculate it. The norm of this phi sub n squared equals pi. So if that means if you take the inner product, so you're doing the inner product sine n plus 1/2 u comma sine n plus 1/2 u is gonna give you pi. Okay, so that can be done. And that can be done really easy. So you can find that integral. So it turns out that if this is true, so if this is phi sub n, so this will be pi, right? So therefore we have the following: the sum of n equals 1 to infinity of G comma phi sub n squared, and all these guys are pi, so divided by pi, so I'm going to take the pi outside, is less or equal than norm of G squared. If the norm of G is less than infinity, so if this guy is less than infinity, do you remember what happens? If you have a series that is convergent, then this guy is gonna go to 0. Okay, so we can say then that the limit of when n goes to infinity of phi sub n, you can say that this guys goes to 0. Well, you can say in absolute value if you want. Okay, we can say that this guy goes to 0, and if this guy goes to 0, then this guy goes to 0, the one that I want. Okay, so because this is inner product of G with phi sub n, because that's what I call phi sub n. Remember phi sub n? Call that guy. So the limit, I'm saying that if G exists, the integral of G exists, the limit of this inner product has to go to 0 when n goes to infinity. Therefore, this guy has to go to 0. So therefore, so this has to go to 0. Since this guy has to go to 0, then limit in n goes to infinity of Snx minus f of x equal the limit of n goes to infinity or the inner product of G with phi n goes to 0. That means the limit of s and x, or in other words, or limit n goes to infinity of s to the n of x equals f of x. Okay, as we wanted, but we are missing one point. So, because we said if this guy is less than infinity, we have this. Okay, so we need to prove that the integral of g is less than infinity. So that's what we're gonna do, and with that we finish this proof. So let me see. So we need to check. So to finish, see how much time I have. 20 minutes, just good. So to finish the proof, we must check that integral of g is less than infinity. And we know that the integral of g, the norm of g squared is integral between minus pi and pi of f of x plus u minus f of x squared sine squared u divided by 2. Why? Because this is the inner product of g with g, right? So you just put that the integral of this f of x plus u minus f of x over sine of u halves times f of x plus u minus f of x times sine u halves. You got this, right? So, and I think I want to, yeah. So du, right? So by hypothesis, remember, our f is continuous. So far, I'm not sure we have used it. Probably we haven't not used it. So I said we're gonna do number one. The number one, f is continuous. If f is continuous, oh my god, look at how the size of my writing has been changing. So since my f is continuous, I don't have really a problem. So okay, so this integral, I need to make sure that this is less than infinity, right? So if f is continuous, I'll have no problem, but my problem is with sine, because I want to make sure sine is not 0. But I'm integrating sine between minus pi and pi. So this is minus pi and this is pi, but it's u divided by 2. So you see everything is set up so it works. So my sine is a normal sine. Just, I just make the period change the period a little bit, but that's my sine. So my only problem really is at 0. Okay. So since f is continuous, because I'm in the case one, the only possible problem excuse me, excuse me, sorry, it could occur when u equals 0. Okay, because if at 0 I had division by 0, otherwise I had no problem, because the function is, one function is continuous and the other is continuous. So no problem, except when the one below can be 0, so I will have division by 0. Then the integral cannot be less than infinity, so I have a problem. So I need to check that that's not a problem. So that's the only point I need to check. So let's check what happens at 0 or at u equals 0. So all I need to do is find the limit. Okay. So I need to find, this is g, right? This is g. So I need to make sure that g is continuous at 0. That's what I need to check. So let's find the limit of g of u when u goes to 0. So I have limit of u goes to 0 of fx plus u minus f of x over u, right? Oh, no, over u, no, over sine u halves, right? Let me put it here. Over sine, well, let me put it here. Sine u divided by 2. That's my g, right? That's my g. But I'm gonna do a trick, a calculus trick to find this limit. So I'm gonna multiply times u, and so I have to divide by 2 by u, right? So, but let me put this guy over here then. Sine u divided by 2, right? So we check if this limit exists and this limit exists, the limit is the multiplication of the two limits. The first limit exists because this is x plus u minus u. So x plus u minus f of x over x plus u minus u. What is it? Sorry, not u, but x. This looks like this first guy, the limit of this guy is the derivative. Where? The derivative of x. Now this guy, I want to say, I can make it, I can make it nicer, but you don't need to do this, but yeah, no, let's do it like that. So let's find the next limit. What is this limit? This limit is, if I plug in at 0, I got 0 over sine of 0 is 0, 0 over 0. How do you find the limit? You find the limit by L'Hopital's. So to find the limit of u sine u over 2, u goes to 0. So by L'Hopital, this is the limit of u goes to 0, and the derivative of u is 1. The derivative of sine is cosine u divided by 2, and the derivative of u divided by 2 is 1/2. Right? So when you plug it 0, you get 2, because this is cosine of 0 is 1, and 1/2 2. So that's 2 times f prime of x. Okay? So this limit is 2 times f prime of x. Therefore, g of u is everywhere continuous, so the integral is finite. Let me put this. Therefore, g is continuous on minus pi and pi, and the integral is finite, and therefore the integral is finite. So indeed, this integral is finite because the whole function is continuous. the integral of a continuous function on a closed interval minus pi is fine. That's if the function is continuous, you can find this integral because you are finding the area, right? So that's no problem. You have no problem with that. The only problem was like, what about if it's not continuous? If you have a division by 0. So this complete the proof. This complete the proof of pointwise convergence for the Fourier series of any differentiable function. Of any differentiable function. Okay, so we are done. That's the end of the proof. So yeah, it was a little bit long. Sorry, look at these notes. I can fix it. I'll fix this. I can make these notes available. Okay, I'm gonna fix this different size of writing, and I'm gonna load these notes in the course materials. So these notes, it gives me a kind of hard time to find a proof that I like, because when I start proving this theorem, I start in this way. There are other proofs, other kind of convergence. Okay, this is not the only convergence you can prove, but I like this proof because it's very natural, and then you start dealing with some problems that, you know, that's why people get famous, right? The Dirichlet kernel and all those things are famous things, but also we got to use this very popular Bessel's inequality. Okay, this is very, very, very important. People prove it in function analysis. So we are using here function analysis, not only analysis, function analysis. So and you see how you had to. So what are these function analysis good for? That's what is this good for? Okay, to prove convergence in Fourier series. Okay, and because you solve so many problems of engineering thanks to that. Okay, so that's the good thing of all that we had done. Okay, thank you guys.